an actual robot with a battery, you can think of it as energy consumption. And you can see here that the DeepRL method is taking paths that are 25% the lengths of the other methods. But basically, at the end of the day, we can see that the DeepRL solution is scalable as the flock size increases. The next few experiments is going to be on robustness. So first thing we're going to see is robustness to observation noise. How this is introduced is we're adding Gaussian noise to the positions of all the entities and then taking the observation on that. But the noise is not actually perturbing the positions of them, just the observations. So on the left-hand side, you have a situation with low noise. So it's behaving kind of similar to the previous examples. But then on the right-hand side, you have something with higher noise. So you can see them shaking all around. If you look at the measured results on the y-axis, again, we're looking at the time it takes for the goal, for the sheep to get to the goal. And then on the x-axis, we have the amount of observation noise or the size of the standard deviation of that Gaussian noise. And you can see that we still take more time than the Pearson method, but it kind of maintains its performance up until 1.2 standard deviation. And then afterwards, it starts increasing, but still about 30% of the performance that we get from Strombaum. But this tells us that the DeepRL solution is pretty robust to observation noise. The next kind of robustness we're going to look at is robustness to changes in dynamics. So we're going to be looking at the flock cohesion. On the left-hand side, we have a flock that's more cohesive. And on the right-hand side, we have a flock that's less cohesive. So it's more spread out. This time around, we're going to be looking at the fraction of the flock that makes it to the goal on the y-axis. And on the x-axis, we're plotting the rho value, which is a parameter of the dynamics. And it's inverse, so the low 0.5 rho is more compact and easier to control, whereas the 4 rho is looser and harder to control. So you can see all three methods perform 97% or more of the flock and get them to the goal. But as you get to about 3.5 and 4, the Strombaum method drops to about 40%, whereas the other methods maintain their performance. But basically, the DeepRL method here is also robust to changes in dynamics. And we've shown that the DeepRL method, after all these experiments, is scalable and robust to the dynamics changes and robust to observation noise. So now for some dirty laundry, the realism of law. I mentioned that we use multi-channel observations, so there's a channel for each entity type. That means, for example, the sheep would occlude other sheep, but they would not occlude the goal from you, so you'd be able to see through them. But other formulations in the related work assume perfect knowledge of position and velocity. So this is kind of an actually kind of a step back. Another thing that we have to address is the shepherding setup that we have is not comprehensive. It doesn't take into consideration obstacles or stray sheep, but we found that by tuning the reward a little bit, you can actually address those things individually. And then the dynamic simulation that we have is, at the end of the day, a simulation. Trying to use this as applicable to the real world is going to have a few speed bumps. It's a simulation, but this is, at the end of the day, dynamics that we found in the related work that we're applying. And then in the context of the mapping that we introduced, that was meant to be a good, you can use this to save you time. We're only showed it on 2 problems in the passive and active agent class. But we actually do have other problems that in mind that this mapping would work for. And we're actually also interested to see if any of you guys can think of any other problems that could be applicable. Another thing is that this mapping is not like a solution to all your problems. There's going to be limitations to this. There has to be some semblance of similarity, even though we're saying it can be different. It has to have some sort of similarity between them to be able to do this mapping. But at the end of the day, we presented this class of active and passive agents that you can map between to allow you to reuse formulations and solutions, and the solutions themselves prove to be robust and scalable. Thank you very much. That's it.
All right, excellent. Very good. And thank you, Azid, for excellent timekeeping during the talk as well. All right, very good. So for our very last talk of the session, we have, I believe, Wenhao Luo, is that right? Wonderful, who's going to be presenting their paper on sample efficient safe learning for online nonlinear control using control barrier functions.
Right. Thank you for the very nice introduction by Hamei. Hello, everyone. Today I will share some of our work on sample efficient safe learning. And this is a joint work with Wenson from Cornell and Ashish Kapoor from Microsoft Research. So speaking of, sorry. Sorry, I don't know what happened. It's not switching. Okay, try again. Okay, sorry about that. So speaking of the model-based reinforcement learning, and specifically we want to target this domain because it's usually sample efficient and very applicable to the robotics task. So the goal of model-based reinforcement learning is usually by the robot interacting with the environment, we want to build a estimation of the dynamics so that we can perform tasks optimally. So this process involves the robot that keep taking some actions, interact with the environment, and receive some observations about the landing state and the cost about having this particular state, taking this particular action, so that we can gradually use some function approximator to help you build an estimation of the dynamics for the robots. And once you have a relatively good knowledge about the dynamics, then the robot could employ some favorite optimal planner that takes your belief of the dynamics and the reward function so that to come up with a reasonable good policy for the robots to optimize this task. And we have seen many successful examples in robotics domain that having the model-based reinforcement learning to teach a car run on a rough terrain, or to show how to teach a 33 degree of freedom's robotic arm to pick up a spherical object. So, but given this nature of the exploration, as you can see, usually the robot could incur some risky situation where things may not always go right? So when the vehicle is learning how to drive on the rough terrain, it actually could easily crash to the side that could lead to catastrophic consequences. So in this case, what we need is some model-based approach that guarantees safety for the robotic system, right? So talking about safe critical control, we usually know that usually requires some knowledge about the desired safety constraint, and then the perfect model or some noisy model of the robot dynamic system so that you know how to constrain the action of the robot so that the robot could remain in a relatively safe set, right? But as we mentioned, usually in order to have a high quality of safe critical control, we usually require either perfect knowledge about dynamics or some conservative estimate of the dynamics, which could be overly conservative if you want the robots to proceed with some task. So in this case, we really think about what if we do not know the dynamics of the robot, how we're able to use data-driven method to help the robot efficiently learn the dynamics and perform its task. So this leads to our objective of this work, which we focus on 3 domains in the model-based reinforcement learning, which first of all is the sample efficiency, second is the safety, and third is also the control performance, right? So initially we want the robots to guarantee safety, not only when testing, but also when exploring the environment. And second, we want the robots to be efficient because the robot can just sit there and do nothing, but it will not help the robots learn anything new about the environment. And with these 2 points, we also don't want the robots to exhaustively search in the space just in order to learn its dynamics. So what we want is the robots doing the learning, they still want to achieve some good performance, right? So with this objective in mind, let's delve into a little bit of details about the concept, the specific question we're trying to solve. So given system dynamics, and we model it by First of all, the nominal dynamics represent your current knowledge about dynamics of the robots, and then plus a unmodeled dynamics. So the unmodeled dynamics here could be model uncertainty or some mismatch of model due to the imperfect knowledge about physical parameters. And we assume the system suffer from addictive Gaussian noise to represent some stochastic. So with that, in this work, we assume that this unmodeled system dynamics could be represented by a linear mapping over a known feature mapping space. So you can consider this phi as a high dimensional embedding representing a known feature mapping from the state and action space towards a high dimensional space of the embedding space. So with that, we are able to represent a wide class of nonlinear system, including autonomous, including the cars or manipulators or quadrotors. So with this assumption, basically how to represent the dynamics of the robot boils down to how to derive or learn this linear mapping of W as a weighting matrix so that we can accurately capture the data of this model dynamics. Right? So when we don't think about the learning for a control problem, if you are given a h time steps, so what you want is to minimize the objective function in this h time steps, subject to, first of all, the safety constraints, representing you want the state of the robot always stay in a particular set. And the second, you want the robots to satisfy these ground truth dynamics. You can easily basically solve this problem by any model predictive controller. But the challenging part is when you do not know the dynamics of D, meaning when you do not know the linear mapping W here, then the robots could run into risky situation or even not perform the task optimally, right? So in this case, what we want here is basically efficiently learned weighting matrix W star so that we can safely optimize the control performance. So with that, we follow the evaluation matrix by the learning community, which is basically a safe learning objective focusing on regret minimization plus safety. So for this one, we're assuming we have a capital T episodes of training episodes. And what we want is to minimize the regrets, representing the difference between all the costs that the robots receive during learning in this total T episodes and the ground truth minimal or optimal performance of the robot if assuming the robot knows the ground truth dynamics. So desirably, you want the robots to achieve some bounded regret so that if you're assuming the T episodes goes to infinity, the robot could approximate to the optimal control performance as if you know the dynamics of the robot. Right? And of course, you want the robots to subject to safety constraints at all times. So the key ingredients that enable us to solve this problem is, first of all, that we use the control barrier function in a stochastic setting to enforce the safety with high probability under iteratively learned model uncertainty. And second, we want to integrate a optimism-based strategic exploring algorithm that help the robots to efficiently guide towards this exploration process. Right. So for many of you may already be familiar about safety through control barrier function, which is a very useful tools. So the main high-level idea of the control barrier function is assuming you want the robots to stay in some particular safe set and whose zero super level set representing by the function h of x. So what you want is to integrate in the dynamics of the robot so that you can find a particular constraints over your controller so that the resulting behavior of your safe function will not decay as fast as a comparison function here shown in red. So in this case, you're able to make sure the robot state H is larger or equal to 0, implying the robot will remain safe at all times. So in this work, we use a stochastic extension for Gaussian noise, right? Because there's due to the stochastic in the robot dynamics, we want to be a little bit more conservative so that the robot could remain a safer condition. So in this case, you can see this little capital delta term representing some conservative estimation of this noise. And with that, we are able to still obtain a set of deterministic control constraints so that to enforce the safety for the robot. So now let's look at a brief overview of the optimism-based safe learning for control. So assuming at any training episode T, we have an aggregated data set which representing the state action pair and the landing state of the robot. So with this information, we can easily use the linear regression or ridge regression to calculate the current best estimation